So the first thing that we look at is the effect that the magnetic field or the current has to produce a magnetic field. What should that be, or what is that? Okay, so what we've learned so far is that if we pass current through a wire or through a conductor, it creates a magnetic field around it, but in such a way that it looks something like this. That, for example, if this is a conductor, that we have, and let's say the current is passing through the conductor like this, then we will have a circular magnetic field around the conductor like this. And of course there's not only one ring, but there are actually multiple rings depending upon the strength of the magnetic field around the conductor. This was identified by carrying out this experiment. So what we did was, we connected a simple piece of wire, passed it through a piece of cardboard, and then we connected a variable resistor, then we connected a switch, a battery, and then we completed the circuit. So when the current was passing through the circuit after closing the switch, and we know this is positive and this is negative, so the current is flowing in this direction. So the current, we already knew, is flowing in a certain direction. So after this, what we did was, we placed the compass in 4 different locations, and we noted down the direction of the needle. So we found out that when the compass is placed over here, the needle points in this direction. When it's placed over here, it points in this direction, and over here like this, and this one points towards that direction. I'm not drawing it inside of the compass because I don't have enough space, but we do get the picture how we are actually visualizing it. This is what we are actually trying to look at. So direction of the current was already known because we had connected the battery. We knew the direction of the current, positive to negative or negative to positive, right? So the compass described, or you can say the compass gave us the visual indication what is the shape of the magnetic field, although we know that it is circular. So the first point that we figured out was that it is a circular magnetic field and it has a certain direction. So you can notice that when the current is flowing upwards, the magnetic field is anti-clockwise. It actually rotates like this around the conductor. But if the current is downwards, let's say in this example the current is downwards, the magnetic field was clockwise. It's actually moving like this. So the direction of the current determines the direction of the magnetic field that is around the conductor. Now, of course, we can't do this experiment again and again and figure out the direction of the magnetic field. So what we've done is we have made a rule out of this observation, and that rule is known as the right hand grip rule. The right hand grip rule. So it works on 2 types of conductors or scenarios or implementations. First, it can work on wires. So the first thing that it can work on is wires, and the second thing is coils. So either the wire is going to be placed in front of you like this. I'm deliberately exaggerating the thickness of the wire so that we understand what the wire may look like to us, or the wire may be placed in front of you like this. So what is this implementation? So for example, if you were to observe the wire from the top, exactly from the top, you will see a circular cross section of that conductor. And similarly, if you were standing at this point and this was the conductor placed in front of you, so the thing that you're going to observe the first time is actually a circle. So these are a few implementations in which the wire will be placed in front of you and you would be required to find out the direction of magnetic field. So even in this case, rather than only being circular, it would be clockwise or anti-clockwise. Now the direction specifically of the magnetic field can be found by right hand grip rule. Right hand grip rule can be used for a wire that is placed over here, and it can be used for a coil. So the coil may look like this to you. I will also show the diagram that how we actually implement this rule for the coil. But the one thing that we need to notice over here is that the rule actually interchanges its function in terms of what the fingers are representing. So the right hand grip rule for a wire, we're going to use the right hand, and if I observe for this wire that I've drawn over here, for example, the current is moving in the upwards direction. So what I'm going to do is I'm going to grip this piece of wire in such a way that I match the direction of current with my thumb. So my thumb of right hand should match the direction of the current. So naturally what happens is that this is where my thumb is, and these will be the direction of my fingers if I try to grab it. Is that so? Do we understand this point? Again, you can try this by trying to grab or hold on to a pen or a pencil that is placed in front of you. So if you try to look at a pen or a pencil, the pointing end of the pen or the pencil may be taken as the direction of the current, and if you try to match the thumb with it and try to grab it with the fingers, you can see that there is a direction how your fingers are curling around the conductor. So this tells me that the direction of magnetic field around my conductor is actually in this way. I'm following the curl of the fingers. So the curl of fingers represent the direction of magnetic field direction. Okay, so but when we, let's say if I change the direction of the current through this conductor, let's say the conductor now is placed like this, but the direction of current is downwards now, right? So let's say that the current is moving downwards. So now it's my job to rotate my wrist, not the full hand but the wrist, in such a way that my thumb points downwards and the curl of my finger tries to grab the conductor like this. Is that so? Right? So the ball point would be pointing downwards, representing the direction of the current. So this is my thumb, these are my fingers. So representing that if a conductor was carrying a current in the downwards direction, it would create a magnetic field that would be in this direction. No, not in this one, but in this one. Apologies. So if I draw, let me draw this again. So if I try to follow the direction of the thumb right now like this, then my curl of the fingers automatically would be like this, from the back of the ballpoint to the front. So it would be circular, but it would be in this direction, right? So we can observe, and of course from this point over here and from this point over here, completing a circle around the conductor, around the piece of wire. So this is how we apply it for a single piece of wire. I will show the diagrams for that as well. And how to apply this for the coils, let's see what we are looking at. So, but in the coils, the rule changes a bit. Over here, the thumb represents the North Pole and the curl represents the direction of current. Direction of current. Right? Okay. So just a moment. Now let's go towards the diagrams for that. Okay, so this is how we're using that rule. So you can see that the thumb points to the direction of the current, and the curl of the fingers right now is representing that the magnetic field should be like this around the conductor, and from the front should be like this. So if this was the piece of wire, then the magnetic field would be like this, and the current of course is the current is moving upwards right now. Do we understand this point?
Yes.
So again, the point of the experiment is to find out the direction of the magnetic field around the wire, but since this experiment can't be done again and again, this one, so what we've done is based on, again, the right hand grip rule was discovered after the observation was made. Students sometimes believe that we already knew right hand grip rule. That's not how it works. We had done this experiment, we looked at the observations, we tried to find a rule to quickly find it, and this is what we come up with. This is what we came up with, right? So it is a rule based on observation. We didn't have it at the very beginning. It was not miraculously revealed to us that, okay, use this rule and then you can find out the direction of the magnetic field. No, it is based on observation. Okay. Now, let's try to visualize for the coil. So this is how we apply it for the coil. Do you see over here the rules or the duties or the responsibilities of the thumb and the fingers are changed or different? Over there, for a piece of wire, the thumb represented the direction of the current. Over here, the thumb represents the direction of the North Pole. And over there, the fingers represented the direction of the magnetic field. For a coil, the fingers represent the direction of the current that is flowing through the coil. Right? Okay. So, as you can see, what I am doing right now, or what the person is doing right now, is trying to align the fingers with what? With the direction of current through the coil. And once he has done that, then if he opens up his thumb, the thumb will be pointing towards the North Pole. And for the coil, what we say is that the magnetic field of a coil actually mimics a bar magnet. So either place a coil or either you can place a simple magnet over there. Both will be having the same magnetic field. Now the problem is that even if you place a coil instead of a bar magnet, then we need to know where the South Pole or the North Pole will be. And to figure that out, we again use the right hand grip rule, as we have found just now that the thumb will be pointing towards the North Pole, right? So over here, if for example, if you had applied this rule, and of course the diagram is inaccurate, this one is inaccurate, we need to have a three-dimensional diagram like this one to eventually apply or use this rule. So if we do apply this rule on this coil, and we eventually find that the North Pole is in this location and the South Pole is in this one, then that would help us to use this or utilize this coil as a bar magnet, which can be used in various applications of varying strength. You see, if we increase the level of current through this coil, then the strength of this magnet will increase. So the current produces this magnetism in the first place. If there is no current in the coil, there will be no magnetic effect in the wire or in the coil at the same time. But if you increase the amount of current, you will see that the magnetic field will become stronger. Now, the one perspective that I discussed with you is represented over here, that if you try to observe the conductor from the very front, this is what you will see. This is the conductor that you may see from the front because it appears as a circular shaped conductor. Now, there are two conventions in this one, and we need to learn both of them because we're going to use them in the incoming chapters as well. So one of the conventions is out of page, and the other one is into the page. When we talk about out of the page and into the page, we are merely referring to the screen that we're looking at right now. Let's try to understand the perspective. So let's say the laptop screen or the mobile phone screen that you have right now in front of you, this is that screen and you're standing at this point. So by any chance, if the North Pole was placed at this point behind the screen and the South Pole was placed behind the observer, the magnetic field would appear to be originating from the North Pole and traveling towards the South Pole. And if I subtend this or extend this concept from this perspective, then the magnetic field lines would appear in such a way that it would look like that they're coming out of the screen that I'm looking at, crossing through your body and going to the respective pole. You are not supposed to remember it in this way. I'm just trying to explain this, how to visualize out of the page and into the page, right? So to represent this from your perspective, if I look at the board from your eyes, so this is what the board looks like. So all the magnetic fields that are coming out of the page, I would be representing them as dots. So all these infinite lines that are coming out of the page from the pole will be represented by dots. So dot represents anything that is out of the page. It could have been current, it could have been magnetic field. So in this case, we're discussing magnetic field. It's possible that if you were standing at this point and you had a conductor placed in front of you like this, and the current would have been moving in this direction for the sake of example, then you would identify this current as current moving out of the page. So do we understand the convention? Do we understand why we use this terminology and where it will help us? Do we understand this point?
Yeah.
Now let's try to go over there on the into the page terminology, and of course the idea would still be the same. This is just for an explanation. You will not find this in the book, or you will not find this online probably. So this is for the sake of example. Now this is the North Pole, that is at the back of you, at the back of your head. This is the screen that you're looking at, just for the sake of reference. There is no screen when we are solving a question paper. So this is the South Pole. Now for the sake of example, if I look at the magnetic field pattern, it looks like that it's originating from the North Pole moving towards the South Pole. This is what we learned in the previous chapter, that the magnetic field lines exit from the North Pole and enter the South Pole, pointing away from the North Pole, pointing towards the South Pole. And if I extend this idea through the body of that person, so the magnetic field line is flowing through your body, going into the page like this. So from your perspective, it looks like that the magnetic field is moving through you but away from you, and it is entering this page or the plane, the imaginary plane that is right in front of you. So to observe this from your eyes, if I were to look at this screen from your eyes, I would have observed that the magnetic field lines are actually entering the screen like this at 90 degrees angle. But to represent this in a dotted cross model, this one would be represented as a cross, and the cross in physics is taken as for the magnetic field and for the current. Right now we're representing the direction of magnetic field, right? So we can take this into the page as a cross. Similarly, if you were to represent current, so right now we're representing current, and over here we're representing the magnetic field as a dot. But if you were to represent this conductor from your eyes, so it would look like a circle, but it would be representing a dot. That would mean that the current is coming out of this conductor surface as viewed by the observer, just the way that we've represented over here. So to represent this on the notebook in 2 dimensions, this is what we were going to draw. A conductor, and at the center we represent a dot. So on this side, for example, you're standing over here. Again, this is a cross representation for the magnetic field, that an area has some magnetic field lines passing through it. So what does that mean, right? So if I look at it from your perspective again, at the back of the screen I can find a South Pole, and at the back of you I can find a North Pole. So the magnetic field lines are actually passing through you into the screen to the respective pole. Do we understand the 3-dimensional understanding of this, right?
Yeah.
Okay, all right. So for example, if there was a conductor placed in front of you and you were looking directly at it, and let's say that the current is moving away from you. How do we know that the current is moving away from me? Let me write this down as an example how the examiner expects it from you. So he's going to connect this conductor in such a way that there is a positive terminal over here and negative over here. It's positive and negative. So we know that the conventional current moves from the positive and comes back to the negative. So this is how he's going to show you that the direction of current is this or that one. But the problem is that he's not going to tell you which one is the positive terminal and which one is the negative one. You're supposed to figure this out on your own. So if I were to connect this conductor with, for example, a small negative terminal and a larger representing positive terminal, this is what it would have looked like. And it would be my job to identify that, okay, this is positive, this is negative, this is the direction of the current, and the current is moving in this direction. He will not tell you the direction of current every time, but he will tell you, or he will give you a hint in terms of placing the battery in such a way that it can help you to identify the direction of current. Do we understand this point?
So just remember that the small terminal represents -1, and
so this is what the current may look like to your eyes, right? To represent this face of the conductor, I will represent this as a cross, and sometimes you will find this as a plus sign in your papers, right? Now, how to draw the magnetic field around such a conductor in which the direction of the current is given? Again, we're going to resort back to the Fleming's right hand grip rule, and over here we have applied this with the help of the hand when the conductor was right in front of us in these diagrams. But over here the conductor is in 2 dimensions, not in 3 dimensions. So what I'm going to do right now is, it's your job or it's your choice how you're going to do this. You can choose any way. You can either just memorize the direction of the dot and the cross, or you can actually learn how we actually find it. So how do we do that is we represent, or we use the right hand grip rule again, but the thumb representing current, because we're dealing with a wire, right? So for a wire, the thumb always represents the direction of current and the curl of the finger represents the direction of magnetic field. And I know this time around that the conductor will have a circular magnetic field around it. So what I'm going to do, since this is out of the page, or the current is out of the page, I will take my right hand, and I'm standing right here, for example. I will take the right hand and point the thumb towards my eyes. The thumb pointing towards my eyes, because I'm trying to match the direction of the current that is coming out of the screen or out of the page right now. Once you've done that, this is what the thumb may look like to your eyes, just a circular face right now. And you will see that if you try to grip this conductor that is in front of you, your fingers will automatically close in such a way. Is that so?
Mm-hmm.
Right? Okay, so this will be the direction of magnetic field around a conductor viewed in this way if it was carrying current out of the page. Right?
And in the other case, you just put your thumb away,
Yeah.
point it away from your eyes, and then you see that
It will be
rotation
counterclockwise. It will be
outside.
clockwise. Yeah.
Yeah.
So in this case, if I try to point the thumb away from my face, if I point it away from my face, then the curl of my fingers actually goes like this. Right? So the direction of magnetic field will be for this into the page conductor in this way. So again, it's not going to change. It's your choice. Either you can directly memorize that the dot is anti-clockwise and the cross is clockwise. You can use the right hand grip rule every single time to eventually figure it out, how to figure this direction out. Now let's try to see whether he has mentioned this in the slides or not. Okay. No, he hasn't. So this is how we look at the conductors from these perspectives, right? Okay. So now let's move on to the next concept that we have, and that is the force or forces among parallel conductors. Forces among parallel conductors, right? So how do we visualize forces among parallel conductors? Now let's say that this is a piece of wire and both of them are carrying current in the same direction. So what I'm supposed to do, let's say for the sake of example, I'm viewing them from the top. So to my eyes, the direction of the current for both conductors will be out of the page. Is that acceptable? Right? So I'm going to draw both of the conductors in this way with a dot. Now, again, I'm going to refer back to the direction that I've already figured out. That's anti-clockwise. It's your choice. You can do that again. Your choice. So it's anti-clockwise, like this. Similar, since it's the same direction, it's going to be anti-clockwise, like this. Now, if we try to compare the magnetic field initiation by each conductor at the center, you can see that the conductor A, for example, and the conductor B, the conductor A is trying to push the magnetic field upwards. I'm only talking about the center. And the conductor B's magnetic field is trying to push the magnetic field downwards. Is that so? Right? If you look at the complete loop. So the magnetic field at the center or the center region is weaker because they are acting against each other. Now let's try to analyze the situation for the outer magnetic field. Now it's your choice, either start from point A or point B. Whatever suits you, it's your choice. So I start from conductor A and I try to move in the direction of, just for the sake of checking, in the direction of the arrow that has already been pointed out to me. And I move in this direction, then I move in this direction, then I move in this direction. So the direction of the conductor A that I'm following, that is being matched by the direction of conductor B. Is that so?
Yeah.
Right? So the center part of the magnetic field is weak because they are acting against each other. But the outer part of the magnetic field is strong. They are strengthening each other because they are moving in the same direction. Or the outer loop is in the same direction and the central loop is in the opposite direction. So what's actually happening is that, or in terms of physics, what we can say is that force is always exerted from a region of strong magnetic field to a region of weak magnetic field. So the external field becomes strong and the internal field becomes weak, so the conductors end up pushed towards each other by an attractive force. So we conclude this from this idea that if the direction of the current is same through the wires, then they will be attracted. And the same idea can be applied. Right now we did the question for the dot conductors. We can find the same for the cross conductors as well. So what's going to happen with these wires, if they are flexible wires, then they are going to appear to you bent like this, because they are actually being pushed together like this. Do you understand this point? Right? But if they are solid wires, then you will see them physically moving towards each other or coming closer to each other. Right? Do we understand this point? Okay. Now let's try to do this with the cross conductors to complete our notes. So let's say we have two conductors, and right now they are carrying current away from your perspective. This is where you're standing and trying to observe them. So to your eyes, those conductors will look like this to you as a circular face. I'm deliberately drawing these symbols differently so that you can remember that into the page can be represented by a cross and by a plus sign according to the examiner. Now let's try to go back to refer this. So we have a clockwise magnetic field around a cross conductor. Let's try to draw that over here. So we have a cross, for the cross current, we have a clockwise magnetic field that looks like this. Now let's try to observe the combined magnetic field at the very center. You see, this one is trying to push the magnetic field downwards and this one is trying to push the magnetic field upwards. So what do we get? At the center, the magnetic field becomes weaker. Let's try to make a loop for the outer one. Now let's start from this side, from the conductor B side, because previously we started from A. Just to verify, does it matter or not? So I start following the direction of the conductor B, and I see that the outer loop arrow is actually matching for the both conductors, right? So the outer loop has a strong magnetic field. Similarly, on the other side, this will be a region of strong magnetic field. As a result of that, what's going to happen is that these conductors will experience a force from a region of strong magnetic field to a region of weak magnetic field. And again, we see that both conductors will be attracted towards each other with the force F. So again, we conclude that if the current is in the same direction for the wires that are close to each other, they will be attracted towards each other. It doesn't matter whether the current is being taken away from them or whether the current is taken or is being brought closer to them. The only thing that matters is that if the direction is same for the current, both conductors will be attracted to each other. Do we understand this point?
Yeah.
Again, the same point will be followed over here, that if there are solid conductors, then they will simply move towards each other, and if they're flexible, then they would be bending towards each other like a flexible wire, right? Okay, so now let's try to do this for different directions of current. Now when the current is dissimilar or the direction is different, so I'm going to draw this directly. So let's say these are the pieces of conductor that are close to you. This is where you're standing and trying to observe them. One of them is out of the page and one of them is into the page. This is conductor A, this is conductor B. Let's try to draw them on this side. So let me draw, okay, so let's draw it over there. So for this one, I will use a dot model for conductor A, and for conductor B, I will use a cross model. I could have used a plus one as well. Okay, so for the dot one, how is the magnetic field? So the dot has an anti-clockwise. So an anti-clockwise magnetic field, and the cross one has a clockwise magnetic field. If you would observe for both conductors at the center, conductor A is trying to push the magnetic field upwards. Conductor B is also trying to do the same job. Is that so? Right? So since the magnetic field is in the same direction, I will say that at the center there is a strong magnetic field. And the magnetic field at the center is strong. Now I'm going to verify this for the external magnetic field. I see that on the outer side I pick A. You can also pick B. It's completely your choice. It will still give you the same answer. So I start from A and I follow the direction of A and I try to complete this loop around the conductor. Now when I reach B, I realize that B is trying to move the magnetic field towards the left side. A is trying to move the magnetic field towards the right side. So on the outer loop, in this configuration, the magnetic field is weak. Weak magnetic field. Similarly over there, we have on the outer side, the magnetic field is weak. And in physics, or simply put, forces are exerted from area of strong region of magnetic field to an area of weak region of magnetic field. So these conductors will basically be repelled from each other. So they're going to be repelling each other, and if they are flexible, they would be bending outwards like this. I'm using the word flexible because I've seen this in a few questions. He asks you deliberately that if the wires were flexible, what would you see? What would you observe? So you have to write down that they would bend. And if they are solid wires, if they are thick solid wires, then you're supposed to say they're going to end up moving towards each other rather than bending, right? So do we understand? And you can do this exercise. What we did was for dot and cross, you can do this for a cross and dot on your own. You will still end up with the same answer, right? Do we understand up to this point? Any issues?
Yeah, I understand.
Okay, so what we have done so far is we have understood that there is a circular magnetic field around the conductor, and how to figure that out instead of using the compass again and again is to use the right hand grip rule. And how we use it, we've also looked at that. Then we looked at this convention of out of the page and into the page. Please be advised, we will be looking at into and out of the page magnetic field later in nuclear physics and nuclear physics and radioactivity. So not only just limit this idea for the magnetic field, but for this chapter we are actually focused on the direction of current, or representing the direction of current. But for the next chapters we will be focused on referring it to the direction of magnetic field. So the dot and cross model goes for both ways, for both type of direction. The dot is something that is coming out of the page at angle 90 degrees angle, right? And the cross is something that is moving into the page at 90 degrees to the surface, right? So these are their three-dimensional perspectives in terms of current, and these are their two-dimensional perspectives in terms of conductor viewpoint. And then we found the forces between two parallel conductors, how they're going to behave and what they're going to look like. Any problems in today's lesson?